So, what are you doing? You've got too many of these open. All right, what I was, remember last, I guess it was, anyway, we went over, last time I think I saw you, we went over the bumping lemma again, and we did it on the board. And then I did that again yesterday with the morning gang. And so whenever it seems clear people aren't understanding things, I go home and make new slides. So I posted on the forum what the page numbers are, and we go through here. We're not going to go over them now because we basically did them on the board, but having two ways of thinking about it, having suppose the guy, this kid knows the first name, and the second kid knows the second name. How much do they have to communicate to in order to know whether the string's in the language or not? Right? So if we go down here to this example, right? The first kid knows the first name, which is 0 to the n, which I've color coordinated purple, and the second guy, and he has to tell the second guy exactly what his string is, right? Because if he doesn't tell him exactly what his string is, then, for example, if he sends the same signal but for 3 zeros and 4 zeros, then he's in trouble because there's a future of 3 zeros and he doesn't know what the answer should be. So I added a bunch of these things, and I think, did we do this example here where the answer is yes, that there is a regular language for it? We did that one. K squared. I think we did not do K squared. All right? So we're just doing various examples here. Suppose the language is just a block of some number of zeros, and you want to know, is that number the square of an integer? And again, the intuition is you have to count them all, because you have to know exactly how many there are to know whether it's the square of an integer or not. And we're not going to go into too many details here because it's a little bit of algebra that's more than we might want to get up for. But remember, the game in general is I come up with an infinite set of first names, which in this case will be a block of n zeros. And maybe I should have used n because it looks like we're using the entire string, but we can always tack on more zeros for good luck, right? So then the adversary gets to choose two of our strings in S, and our job is to prove that those two strings, our job is to prove that every pair of strings are distinguished, and we're going to do that by the adversary giving us a particular pair and showing that they're distinguished. And how do we do that? Well, the adversary gives us some number I of zeros and some number of j zeros where I and j are different. I thought we were going to sort them, in fact, but oh yeah, here we go. Right, without loss of generality, assume that j is the big one. All right, and then our last name is going to be tacking on to either the I zeros or the j zeros, right? We're going to tack on some number of r zeros, right? And then we want I plus r to be a square, and we want j plus r not to be a square, right? And so that's how we're going to make the one a square and the other not a square, right? If the one is a perfect square, then it's going to be a yes. While if the j plus r is not a perfect square, then it's going to be a no, and that's going to distinguish are alpha and are beta, right? And hence it'll follow that that the infinite set of strings, first names that we have, is in fact all distinguished. So they all have to go to unique states, and hence the number of states in a DFA has to be infinite. All right. So yes.
So if you just go back,
We certainly can. That's the joy of.
So am I able to say then, if language alpha is not equal to language beta, that means that they're both different.
But what's different?
Alpha, right? The language inside alpha and the language inside beta, or sorry, alpha's in one language, beta's in another language. I can say they're different.
All right. I don't like too many of your words. So first off, when you're doing anything in life, it's really important to do getting correct types. So you're talking about alpha being a language and beta being languages. They're not languages. They're strings.
No, what I'm saying is right here.
Yes.
Here. The bottom line is they can't be equal.
Yeah. We need that one of alpha sigma is in the language, and the other one, the beta sigma, is not in the language. We could have switched it the other way around. So alpha sigma is the first name, last name sort of deal. And they have to have different answers in the future. So alpha and beta have to be distinguished in distinguished states when they've read in, because when the sigma comes, if they were in the same state, sigma came, it would put them in the same state of the DFA, and that would be bad because then they would be given the same answer for alpha sigma and beta sigma, and we want them to have the language wants them to have different answers.
Yeah. Okay.
Yeah.
So unique, basically unique, right?
Yeah, unique. So here's just a little bit of how we could do some simple math. We know j squared. Remember, we have I and j. If you square j, then that is a perfect square. And if you subtract off I to make r, then I plus r becomes j squared, which is a perfect square. And then you have to do a little bit of math to prove that that j plus r is not a perfect square, but we don't need to get into that. Here's another example. We have the string is the language consists of strings where if you cut them in half, you get the same omega appearing twice. All right? And again, it feels that if you've read in the first omega, you have to remember, not only do you have to remember, it's hard enough to remember the length of omega, but now you have to remember exactly what omega is, right? So that's clearly not happening. But the reason we're doing this example is because we're going to run across a bug. Various bugs do come up. So the obvious first name is to have it be omega, an arbitrary string, and then alpha and beta are two arbitrary strings from our set of arbitrary first names, and then we're going to make the last name be the alpha, right? So that seems like we're really doing fine, right? Alpha sigma, which is alpha, is clearly in the language. It's clearly a yes, right? But beta is different than alpha, so it should feel that beta sigma is a no, right? That feels like the way it should go. But sometimes, yes?
Beta could be like 7, and alpha could be 5, so it could be 12, it could be 6 by 6.
Where did you come from? You are fantastic. I have slightly different numbers, but the same idea. What happens if alpha is 2 zeros and beta is 4 zeros, and then beta sigma, which is really beta alpha, is going to be it's going to be 6 zeros. And if you cut it in half here, then it feels like that the first half and the second half aren't the same. But that's not where you cut it in half, right? As brilliantly was stated, you set it in half so that we have 3, 3. Right? Everybody see that? So sometimes it's not absolutely clear that the answer is no. Like even in that example where we did the squared, we fudged so that the yes wasn't a square. But you do have to do some fancy math to prove that the beta sigma was not a square. Right? And it was just showing that it was it was squeezed between two different squares that just weren't happening. All right? So we're going to try again. And actually, it comes down to, that the middle what isn't well defined. Right? So we want to somehow make the middle defined. And the way I'm going to make the middle defined is I'm not going to, when I talk about, remember, I get to come up with an infinite set of strings to be my first name. And it doesn't have to be all possible first names, right? It needs to be a set that's infinite, and every pair of them are distinguished, all right? And the ones that gave us a problem before where the strings were all zeros, but let's just say that our first names are 1 followed by some number of zeros. And that 1 is what's going to be acting as what's in the middle, right? It's going to dictate where the middle is, right? So then the adversary is going to give us an alpha and a beta, which is, of course, 1, some number of zeros, 1, a different number of zeros. And we're going to play the same game we did before. We set sigma to being alpha, and clearly alpha sigma, alpha is a yes, right? But now, you look, beta sigma is going to be 1 followed by some number of zeros, 1 followed by some number of zeros, and those zeros are different, right? So there's nowhere that you can cut it in half. And I mean, either if you cut it where we want to expect to cut it, then the I doesn't equal the J. And if you cut it somewhere else, the ones are going to mess you up. Right? Does that make sense? The usual crowd is nodding their heads, so I'm going to hope that means we're good.
So the previous example, when you had alpha with the zeros in the previous one.
Yeah.
How many total zeros is that?
Well, we would have I plus j zeros, or here's j plus I zeros, and if I plus j happen to be even, then you could cut it in half and have it be of the form omega mega.
Oh.
Right?
Okay, so you just look at even for it. Okay.
Yeah, so the key is we were thinking, right, our beta was, do I have this beta alpha? I think I have these two switched. This is a typo. The 4 should come before the 2. I may remember to fix that, but I may not. Everybody, yeah?
So I'm just a little confused here. What language does the bumping lemma accept? Or it says no DFA solves the language.
Yeah, the goal is to prove that omega, the language consists of all strings such that if you cut it in half, the first half is exactly identical to the second half. That language can't be done by a DFA. Can't be. Right? And the reason is, now, if all the megas were zeros, then it's just asking, is the number of zeros even? Which can be done by a DFA. Right? So we got to use the fact that the megas aren't all 0. So what we did is we let it be a 1. We only considered, our goal is to prove that the DFA doesn't work. So we have to find one input in which it doesn't work. And we get that input to be whatever we want it to be. Right? We don't have to consider all possible inputs. we consider just those inputs that we like, right? So we're going to narrow our focus down on inputs of the form, where did it go? 1, a bunch of zeros, 1, a bunch of zeros, right? And our quote first name is the 1 in the bunch of zeros, and our last name is the other 1 in a bunch of zeros, and then we're right back to the beginning of are those two blocks of zeros, do they have the same size?
And they could and they couldn't.
And they could and they couldn't, but if you don't count them, if you're a DFA and you don't count the number of zeros in the first half, right? If you don't have an infinite number of states, then you can't count them. So then you'll be confused. There'll be some alpha and beta that will go to the same state.
You lost.
All right, remember, the big picture was our fine Catwoman claims that she has a DFA that solves the problem, right? And so we have all these first names, and we first run 0, 1 somewhere, and it lands here, and then we run 0, 1, 0, 0, and it lands here, and we run 1, 0, 0, 0, and it lands here, right? And we do that for all infinite number of first names, right? But we only have, this is a DFA, and the F stands for finite, right? We only have a limited number of states. So there are two strings, alpha and beta, that go to the same state, right? And what string is that? Well, it's alpha. Let's call them alpha and beta, and let's call it 0 to the I and B to the J, right? And the problem is that if you have a sigma from there, I've learned just to draw a squiggle. Is it a zeta? That looks like more like a zeta. This whole thing here is a zeta the whole time? Are you sure it's not a sigma?
Sigma is the sun.
It's a pi.
Well, I can't draw either of them. Psi? Sigma? Psi? Sigmas? In my brain, this is a sigma now, so the chances of it switching as it comes out of my brain is pretty small. But anyway, whatever that is, right, we have some future, and alpha, those two, the alpha psi and the beta psi are going to end up at the same place. So the machine's giving the same answer for them, right? But we note that the language is giving different answers to them.
No, it's actually a sigma.
Is it a sigma?
It's a sigma.
Oh, good. Saved. And do you know how I probably knew it was a sigma? Is when I typed it in, I probably had to write the word sigma at some point. So that's good, because my brain never would have switched that.
No, it could be a zeta too. Yeah, they look similar.
They look similar. Let's go for sigma, because I know psi is something like that too. They're all they're distinct scribbles. All right.
Question.
We have a question.
The previous example, the recent one, what if the number of zeros becomes odd? How would that change it?
Well, we have these ones here, which is marking the middle.
The previous example.
Oh, the previous example was just a bug in our proof, right? So it's a buggy proof, and it doesn't mean anything. It just means our proof was buggy. So we had to come up with a proof that's good, and this proof here is good. Yes.
What if it's odd? Are we rejecting that, or it doesn't matter?
If it was odd, our proof would have worked. But we can't count on it being odd. The adversary is going to make our life as hard for as it can. So if the adversary can make our proof buggy, it will. And you said something, and I don't know what it was. Previous.
That's the previous example.
The bad one with the zeros.
What happened to the double alpha?
alpha, alpha, say, what if alpha was 2 zeros and beta was 4 zeros?
But what if it's just alpha alpha?
Oh, alpha is a yes no matter what. Right? I'm not debating alpha being a yes. Right? So that's a yes. It's the question is, did we get a no here? Right? And if it was even, then this would have been a yes and they would have both been yeses. And that would have been fine because over here we could have had this been an except state and everybody would have been happy except the adversary would have been happy and we would have been bad at finding counterexample to this DFA.
So for in this case, you found one example that doesn't work, right? I mean, because they both don't distinguish. I mean, they're not distinguished.
They're not distinguished.
So for the beta alpha, they end up being even then. So which solves that language, right?
We haven't proved anything about this language other than that our proof didn't work.
Right.
Right? So this proof doesn't work.
Right. It doesn't work.
Yeah. I mean, the language, there's still no DFA that solves this problem.
Yeah.
It's just that this proof doesn't work. And in fact, as I said, if we got rid of the ones and we only talked about omega being in zeros, then there is a DFA because it's just asking, is the length of the string even or odd? All right, so here's another I'm just giving you some little tricks now. You tweak it a little bit, and suddenly life becomes different. And so we want to see, let's say we have, the string has 3 parts, a u, an omega, and an omega, and the u and omega can be any strings, right? So you think, what are we going to do? Well, I get to choose what the input is. So I'm going to just choose the u to be empty and continue on as I did before. Right? This is exactly what we did before. And life is good. Right? But can you come up with their bug?
With this?
Yeah, there's a bug in this. Somebody. It's the alpha. Alpha is clearly a yes still. But how can this be a yes as well?
0.
0 is a good number.
No. What if the I, J are the? Can we make it the same? No, we already did.
So in general, we want to prove that for every I and j, this is a yes. Right? We just say it has a u and omega and omega, right? Why can't this entire thing be our u? Right? And have no omega at all. Right? So this is a yes too by setting u to be setting u to be this whole thing and having omega be the empty string, and then everybody see that then this becomes a yes. Right? Right? I claim this string here is a yes string. Why is it a yes string? Because I let u be the string in question, and I let omega be empty.
What is the answer of the language? What is the language?
The language is the set of strings that it's the set of strings that are formed by taking any string u and then taking any string omega and going u omega omega, right? The question then, is there a DFA that solves this problem? In fact, what is this language? Tell me a string that's not in this language. Yeah, see? That's the problem, is every string is in this language. Right? L is regular. Why? It's everything. Why? Because you just set omega to be empty, and then u gives you everything. Right? Does that make sense?
Go back, please. To that last line. That omega is empty.
Yeah.
How did it end up being not?
Well, I mean, I'm claiming that every string has this form. You give me your favorite string, and I make you be that string, and then I made omega to be the empty string, and then you can be anything, and then the language is every possible string.
But can omega be anything as well? Are we let?
Just by setting omega to be empty, I already have gotten every string in the language, right? So if every string in the language, then clearly it's regular. How is it regular? The DFA just says yes, right? As a start state with a yes, and it just says yes, right? Sometimes it's nice to have a yes man. It's nice to have somebody like you who gives us a little grease, but it's nice to have somebody who just says yes, yes.
Yes. Yes.
Excellent.
I have a question. How are you able to assume that omega can be an empty string? Is it because of the clean star effect?
I'm claiming that every string can be made to be of this form by making omega 0, empty string.
It says that omega there and you can only be 0 or 1. Clean star.
Yeah.
It can be 0 or more, 0 or 1. And because it says 0 or more, 0 is saying it can also be an empty string. Yes?
So take this string, take this language and restrict it by forcing omega to be the empty string. If you restrict it, you get everything. Right? And everything is, if you restrict it and get everything, then you must have had everything before you restricted it. Yes?
So, like this string is u followed by a repeating part. And if you set that repeating part to be empty,
Yes.
u,
Yes.
u is everything.
Exactly. Exactly what we were saying. Everybody good? All right, so now we fix it by putting the pound sign, the hash sign between the omegas. Now what do you think? Is this guy regular or not regular?
What the heck is the pound sign? What does that mean?
What do you call that symbol? Hash, pound, number sign.
Regular. You do the same.
So how many people think it's still regular? How many think it's not regular anymore?
Not in the alphabet.
It's there. I have it there in my string.
You make a known, you make a start state that is not an exit state. You loop zeros and one, you still make omega empty, and then you get a transition hash.
Yeah, but the hash, I mean, let's see what this language is. I'm claiming this language is it's the same as the set of language where there's a hash between the two, right? Oh, here, does it make a difference? That was our question. And this one's not regular. This asks, it's a set of all strings where there's one hash in it somewhere, and that hash has the property that whatever's after the hash is a postfix of what's before the hash, right? And that's actually hard because when you remember this, you're going to have to remember that whole u omega part because you don't even know which is the u and which is the omega. And then when you read the second part, you have to check to see whether it's a postfix of what came before, right? Right. So here's this here is a postfix, and this here is not a postfix, right? So this is a yes, and that guy's a no. Right? Does that make sense? Yeah?
No. Can you explain that again?
Which one? The mega? The u omega, the mega is not regular.
Because we don't know what the first mega was, so it depends on the first one.
Yeah. And the u omega was regular, and now u omega hash omega is not regular.
Is it the same reason because we don't know the first mega?
Yeah, and we have this we have this hash which cuts things. It helps things a lot to have something actually mark the spot in the middle. Did we have another question here?
Yeah, so now the first omega is U, right? U itself is the first omega.
No, here, I mean, in this example, U is 1, 1, and omega is the 3 zeros. That's why we have a yes here, right? But in here, there's nothing that the U and omega could be, right? The omega has to be 4 zeros, but there's not 4 zeros here. So that's why this is a no.
Okay.
So why can't you just take the omegas and strings again?
Well, do you understand why this is a yes and this is a no?
Not really.
Right? Well, if omega is the 3 zeros, then the first part has the form U. The U can be the 1, 1, and the omega can be the 3 zeros. And so this is of the form U omega omega with a pound in between. So this is a yes, right? But this one is a no, right? Because after the pound, this has to be the omega. Whatever's after the pound is the omega. And then you ask, what's before the pound is omega postfix of it, right? Is it U omega? And no, here we only have 3 zeros, so it can't be an omega there. Is that making sense? Kind of? Yeah?
So if we replace the U with, so you know how it's 1, 1?
Yeah?
If we had 0, 0.
Yeah. If this was 0, if this was 4 zeros, then, or 5 zeros, then both of them would have been yes. Right? Because 4 zeros, and then there'd be at least 4 zeros.
How would we differentiate between U and omega if they're all zeros?
Well, here's the algorithm. Here's an algorithm for telling me whether it's in the language or not. First check, is there only 1 pound? And if there's only 1 pound, then let omega be whatever's after the pound. That's what omega has to be after the pound, right? And then see, is omega on the end of that, right?
No, I just understand why. As I was able to say where we could make omega empty and then say,
Right.
it's because of the hashtag. It can be a part of U.
Yeah, the hashtag dictates what omega is going to be, right? So we can just do the same proof where we did before. Now we can say let U be empty and S be strings of zeros, and then alpha and beta are strings of zeros, and then let sigma be pound alpha. So now alpha sigma is alpha pound alpha, right? Because the sigma is pound alpha. So alpha sigma is alpha pound alpha, which is a yes, right? It's a yes when U is 0, is empty. Well, here I assumed that the J was smaller, right? If the J is smaller, then having I zeros isn't a postfix of having J zeros. You don't have enough zeros, so that's a no. People following this? So, before I go on, let me want to remind you that this proof has 2 parts in it, right? There's the part where you prove the bumping lemma by putting strings or by putting every first name to a state. There's that whole idea, and do you understand it? And you should be able to at least state the bumping lemma and be able to give intuition about why the bumping lemma is true, and talking about states and stuff. A little discussion about it. And then the third thing you have to be able to do is, given a language, use the bumping lemma to prove that language is not regular. Oh, and then of course the next thing you're going to have to be able to do is I give you by mistake, I give you a language that is regular, and you're going to have to say, oh, I'm not going to prove that that's not regular because it is regular, right? You have to be able to identify regular and not regular. All right? All right, so we're going to do one last example, and for some reason I had this example as our very first example, but when I was doing it in the morning class, I found out that, hey, actually this example is pretty hard. So we're gonna do it now and see how people do. All right? So again, the obvious thing is to have the first name be the zeros and the last name be the ones. So the set of first names is the set of all possible zeros, and then our adversary gives us an alpha and beta that are different numbers of zeros, and then we're going to let sigma be some number of ones. All right? And how many ones do we want? Well, remember, we want 0 to the n, 1 to the m be a yes, and we want 0 to the n prime, 1 to the m be a no. All right? And so, in order to get a yes, you have to have this exact equation. Right? So you go up there and you say, great, let's make this a yes. How do we make it a yes? As well, we choose m so this equation works out. Right? And then it looks like we're done because this is a yes and this is a no. Right? Well, I mean, if m and n and m have this relationship, then n, which is different, is not going to have this relationship. So it's going to be a no. Right? Everybody buy this? All right. Everybody get what the language is. It's a bunch of zeros followed by a bunch of ones where the number of ones and zeros has this exact relationship. All right? So if we set up the first names as we have all along, and we set up, and then we're given the alpha and betas, which are different as we have all along, and then we get to choose how many ones we have, then we want alpha sigma to be a yes, right? And what's alpha sigma? Well, it's this n zeros and m ones, so we get to choose m, so we have m to have this form. And if you plug in m that form, then bang, we get a yes here, right? But if the number of zeros is different, then it doesn't have this form, and that would be a no, right? Are people following this? Yes.
Show me like directly how they're different when we put something for n and m, and then when we.
Well, given this m, there's only one n that works, and that n is this n. And this is a different n. So it can't work. Right? Does that make sense? So we make this, that's the general game, is we have a set of first names, we're given two arbitrary ones, we choose the last name to make alpha sigma a yes and beta sigma a no. Right? And you have to work sometimes to make the yes or work to make the no. Well, here we work to make the yes by doing this. And then the no just fell out because what? Because it's a different n. It's a different n. How do we know it's a different n? It's because right up here, alpha and beta are different.
What if there's a different, so you know how there's different n's? What if there's different m's as well?
Well, there's not, because I come up with one m for the two of them. And we look at alpha sigma and beta sigma. So the m is the same. Right? Is that making sense? Everybody buying this example? Everybody see how the proof goes? It's pretty standard, and you should be able to do it on a test, say, for example, on November 6th. Yes, question?
To verify, is it okay if we
You mean making this one a no? I didn't really know.
Let's say alpha was instead of 1, and sigma was instead of 0. And beta was instead of 1 to the m prime, and then 0 was, sigma was 0.
Well, our language has the zeros first.
So we always have to start with whatever.
I always do first name, last name. Yeah. So he wanted to switch the role of first name and last name, and I'm saying the first names are first. And that's just the way there is. So everybody happy with this proof? It's really a standard proof like we've done a million times before, except there's a bug in it.
With first name, the concept of first name and last name work if they're like 0 and 1 and 0 O's or something? Like, 3 different ways of, 3 different parts.
Yeah, well, we did the A plus A's equals A's, and that had different parts, and you got to choose how to break it up.
Oh, so we just always split it into 2, no matter how many there are.
Yeah, because the proof technique has 2 pieces. In fact, the pumping lemma, I don't even remember what it is, but it splits it into more pieces, and it does hairy things. So we're not going to do that. All right. Nobody see what the bug is?
For some ends, isn't n going to be negative?
Yes! There are 2 problems. For some n's, it's negative. And, I can bump that up by making, but for some n's, it's not going to be an integer. Right? Dividing by 5 has a real bad habit of making things fractions. All right? So how are we going to fix this problem? Exactly. We're going to limit the n's, right? So we want to make m this, so we got to go back, right? Where are we doing here?
Wait, we found a bug?
Yeah, we did find a bug. The bug is that n minus 7 divided by 5 might not be positive and might not be an integer.
Because what? We can change the n to be negative.
Because the n could be anything. N could be 2, in which case it's negative, or n could be 14, right? In which case it's right. So yeah, let me figure out what we're doing first. Here we go. I think, so I'm on 226, but there's a danger in that I was taking slides from this later section to move them forward, and I think I messed up the slides in the process. So when I get home, they get renumbered all the time. So anyway, let's. So what we're going to do is one option is to let this block of zeros be limited, right? We're going to let the first S be a set of first names, be only those n's for which n minus 7 over 5 is a positive integer, right? And then when our adversary gives us an alpha and a beta, the alpha and beta will both have this property that it's a positive integer. And then we're very happy to set m be n minus 7 over 5 because we know it's a positive integer, in which case then the proof goes through before. Right? Right? I get to choose the S, and then the adversary has to choose the alpha and beta from my S. Yeah?
You said somewhere that like the formula n equals 5, n plus 7 is linear, or like 1 to 1. So like some formulas will be more than one answer.
Yeah, and in fact, I think on the homework problem, there's one where n equals n minus 100 squared. And then you have this danger of there being, that can be true for n and n prime, which are different. or maybe it was the other way around. This squared equals m, right? And then these two different things that was what it was. These two different things can give the same answer, and you have to deal with that somehow. So yeah, here we're definitely using the fact that the problem is linear, so that this is definitely a yes because we made it a yes. And then if you plug that there's only one end that works to make a yes, and so you're going to get a no.
Should we like state that in the proof? That should be said somewhere, or we can just kind of leave it in hope?
I think if you were to state it and I was marking it, I would, and everything else was perfect, I would probably give you 110 for it. I'd say, hey, well done for thinking about that and commenting on it. I probably wouldn't require everybody in the class to get it because they won't. All right? But certainly, you're right. If this was our equation, right, if you had nonlinear things, then it would be extra problems to deal with. And if I'm not, is this on the homework assignment? Not the homework, the practice things that are on the web. Yeah. I don't know if it's there or not. It's certainly one I have given in the past, and it's harder. Right, so the point is, S is a seventh the size it was, but that's still infinite, so that's no problem. Here's a second fix, and we don't need to get into it exactly, but the second fix is all these, if we stick with all of these first names, all the zeros strings, they're still distinguished. And the way you can distinguish them is by having your sigma tack on a few more zeros for good luck. Right? If the number of zeros here doesn't have the n minus 7 over 5 property, you can make it have that property by putting in more zeros in the sigma, so that these slides are getting crazy, so I'm not understanding these slides. It's some you just put some extra sigmas here so that it all works out, and let's not worry about it. It's getting an example that's a little complicated for the bulk of the people in the room. And all right, I'll go through those last slides and make sure they're right. They seemed a little bit wonky there, partly because I kept editing things, and then they're wonky. All right, so we are now done. We're done Turing machines, and we're done regular languages. All right? So the next topic is context-free grammars.
And what about DFAs? Are we done with those?
Regular languages, we're done. DFAs, NFAs, regular expressions, we're done all of those great things.
So all these topics are going to be in the midterm on November 6th?
Yeah, so what's going to be on the topic exam on the midterm of the exam I've made so far, and I may change the questions. It covers what we've done up until today, and then it has one question on it from context-free grammars. All right, so I'm going to hold with me 1 second.